Hi guys, we're going to continue with complex numbers. This is the fourth session. In the last three sessions, we have seen the introduction to imaginary and then to the complex numbers. We have seen what is the meaning of it. In the second session, we have seen how the complex numbers are added, subtracted, multiplied. In the third video, we have seen an introduction to Argand plane and how complex numbers are plotted in the graph. We're going to continue with the same idea, and we're going to now look at the continuation of polar coordinates of z, which is a complex number. Right? So that's about me moving forward. Right, so we're going to look at something called as a vector form, which we already saw in the previous class or in the previous video, but we are going to add a few more points to what we have discussed in the last video. So we have seen that a z, which is of the form a plus ib, this is called as a rectangular form. Okay, this is a rectangular form. This can be converted or can also be represented in this form, and this is called as the polar form. And in the last video, we have seen why this conversion is happening, how is it possible to write it. And we have also seen that there is a third way of representing it, which is the exponential form. Okay, this is the exponential form. So we have seen the three forms of representing a z, which is a complex number. So today we're going to see how to find the negative of a z. What if z is given to us and we want to find and plot the negative of z? It's a very simple idea if you understand what is happening. So let us take this point. This is what? 3, 2, correct? This is your z, which means your z is 3 plus 2i. Now I want to find negative z, which is nothing but negative of 3 plus 2i, which is negative 3 plus negative 2i. Right? So you have to plot this. So negative 3 is here and negative 2 is here. So my negative z, this point is my answer. So my negative z will be like this. And you can notice that your z and negative z are exactly opposite each other. So there is a 180-degree difference between them. The length, whatever is here, r, will be the same length here, r. Because mod z, according to the formula, if you remember, is 3 square plus 2 square. And mod of minus z will be root of minus 3 whole square plus minus 2 whole square. So both are same, it doesn't change. The only thing that changes here is the angle. So the original angle, if you notice, original angle of z, this would have been your theta. Now for negative z, the angle will become theta plus 180 degrees. It means the mod of z will be equal to mod of negative z. The other thing you'll realize or notice is z and negative z are mirror images with respect to the origin. Mirror images with respect to origin point, single point. Okay, and the third point you will notice, the first point, second point, and the third point. The third point you will notice is if the argument of z is theta, then argument of minus z will be theta plus pi or theta plus 180 degrees. Right? The next thing we will notice is what happens if I'm looking at, if z is given to me and if I want to look at 2 times of z or half times of z, what happens then? So if this is your z, let us say this is 2 or rather 3, 2. This is your z, which means your z is 3 plus 2i. So 2 times or half of z, so 2 times of z will be 6 plus 4i, which means if I want to take 6 plus 4i, you will notice I will take a red color and mark. 6 is here and 4 is here. So this is your point. This is your point over here. So the new z, which is 2 times of it, if you notice, will overlap with your original z. So exactly what is happening is that theta is same for both. The angle or the argument is same for both. Only thing is it is stretching. You're just stretching the vector. You're just stretching the z. Similarly, half z will be 1.5 plus I, which will actually, you will notice 1.5. If I use a green color, it will be very evident for you. This is your 1.5. So, and 1. So this is your z, like this. And here you can see again the angle or the argument is same, but the vector became contracted. So when you take a z and make it as k times of z, you are either contracting it or expanding it depending upon the value of k. Depending upon the value of k. If k is negative, you are also reflecting it. You're also reflecting it, because if I tell you, if I say z is like this, if I say z is here, this is your z, which is 2 comma 3, which is z equal to 2 plus 3i. Now if I ask you to find minus 3 times z, basically first you have to reflect it. So it's very easy. First reflect and get a z. So your z will be minus 2 and minus 3. So minus 2 and minus 3 will be here. So this is your z. Now this you have to expand 3 times. So the expansion form, when you do this, if I draw it in red, will be very lengthy like this. Like this. So this is going to be your negative 3z. Okay, so this is how your manipulation of z happens when you're simply multiplying with a constant. The next thing we're going to see is what happens when you're adding two z's, z1 and z2, or when you're subtracting two of them. So first let's look at the addition. Let us say I have a z like this, which is your z1, and I have a z like this, which is your z2. Okay, now addition of z1 plus z2 means it is the addition of these two vectors z1 and z2. Now in a vector, the starting point is called as the head and the ending point is called as the tail. Let's call it as head and tail. So when you're supposed to add the vectors, what you're supposed to do is you keep your first vector as it is, which means z1 don't touch. z2, take it and keep it and attach it like this, in the same direction. Okay, this is your z2. So the head of z2 will be touching the tail of z1. The angle should just transfer this from left hand side to right hand side. Okay, so that's what you're doing. And finally touch the origin to the end point of z2. This will be called as z3, which is z1 plus z2. Okay, so once again, what happened exactly? I took z1, on top of z1 I put z2, and then finally the head of z1 is being added, or I'm drawing a line from the head of z1. Okay, if I draw it in green, from the head of z1 I will be taking to the tail of z2, and this will be called as z3. This is going to be called as z3. This is how you add z's in the graph. Normal rectangular addition, we already know how to do this. It is going to be a1 plus a2 plus I times b1 plus b2. This we know. For subtraction, a similar logic will apply. If I take this point as z1, if I take this point as z2, and I want to get what is z1 minus z2, so I can convert this as z1 plus minus z2. So I'm changing my subtraction into addition. So I will first have to find out what is negative z2. Negative z2 is easy for me to find. So negative z2 will be here, mirror image. This is my minus z2. Now I have to add minus z2 and z1. When I'm supposed to add this, so basically what will I do? I will bring this graph and put a tip from the tip of Z1. I will be drawing like this. So this is my Z2. So in fact not Z2, it is minus Z2. So now finally, when I take from the starting point of Z1 and draw a line to the end of your Z2, the result that I get, this is going to be called as Z1 minus Z2. This is going to be called as Z1 minus Z2. So this is the subtraction part. This is how vectors are subtracted. Okay, but most often than not, if we deal with the rectangular coordinates, our job will be done. In particular cases where you need to understand how the graphical representation is happening, you also need to understand the theory that we just discussed. Right? The next thing we're going to talk about is distance between two complex numbers. So if I say Z1 is given to me over here and I have a Z2, which is like this, then the distance between Z1 and Z2 is described or defined as modulus of Z1 minus Z2 or modulus of Z2 minus Z1. It is a difference between the two and its modulus. Okay, and if you look at the rectangular form, it is nothing but a1 minus a2 whole square plus b1 minus b2 whole square, because your Z1 minus Z2 becomes a1 minus a2 plus I times b1 minus b2. If you take it as Z2 minus Z1, then it becomes a2 minus a1 plus I times b2 minus b1. So if I take modulus means square of the first part, real part, and square of the imaginary part under root. So it is root of a1 minus a2 whole square plus b1 minus b2 whole square. Now whether I write it as a1 minus a2 or a2 minus a1 whole square, it is the same because you are just squaring it. So you can see that mod of Z2 minus Z1 or Z1 minus Z2 both mean the same. So the distance between two complex numbers is nothing but the square root of the difference of their real parts and the difference of their imaginary parts squared and under root. Okay. So graphically, we are basically looking at if this is your Z1 and this is your Z2. Okay, this is your Z2. This is the distance between them. Okay, this is the distance between them. Right? So it's pretty self-explanatory after that. I mean, whatever I showed. This is normally like a coordinate geometry only. So this is A1 plus IB1. Or if you write it in the coordinate form, it is A1 comma B1. And this is A2 comma B2. So if you want the distance, then I will create a triangle here. The hypotenuse is what I want. This length is basically A2 minus A1. And this length is B2 minus B1. Correct? So my distance or the hypotenuse square is A2 minus A1 whole square plus B2 minus B1 whole square, or H, which is nothing but your hypotenuse, and you'll get the same formula. The last part we're going to discuss about in the vector form is the midpoint of two complex numbers. So if you have two complex numbers like this, Z1 and Z2, the midpoint is given by Z1 plus Z2 by 2, right? It is similar to coordinate geometry, very similar to coordinate geometry. So the formula is average of your real parts and average of your imaginary parts. That becomes the midpoint. Graphically, it's no different. It's the same. So if I take Z1 here, Z2 here, join the 2 points and the mid one, this point will be called as Zm, which is the midpoint. Okay, so it is exactly same as coordinate geometry, no difference at all. Okay, so these are few things which might be useful to us in solving of problems or understanding complex numbers. In the next session, we are going to take up few more topics, few more interesting areas about complex numbers. See you in the next session. Please go through all the things that we have discussed once again.